Hello and welcome to part 2 of the Graphene series. This time we talk about the Wigner-Seitz cell. What we want to accomplish this time is to review some relevant aspects of the conventional unit cell. Then we'll construct the Wigner-Seitz cell for graphene in real space. What we want to do is to calculate the electronic structure or band structure for graphene. For band structure calculations, a primitive unit cell will be required. Question: what is a primitive unit cell? Before we get to that, let's review unit cells in general. Remember that it's not unique. There's more than one way to define it. To describe a crystal structure, we choose the most symmetric unit cell possible. That way we describe all of the group and translational symmetry in the crystal. Also, accurate descriptions of the crystal structure rely on a proper choice of the origin. So in the example below, there are 3 unit cells there out of many possibilities for this 2D structure with 2 atoms. The square choice is best because it represents all of the symmetry present, inherently present in the crystal. Accurate and appropriate representations of the symmetry of a crystal are essential in calculations of its physical properties. So we'll be coming back to the topic of symmetry many times during our study of graphene. Unit cells we normally work with are called conventional unit cells, and those are either parallelograms if they're in 2D or parallelepipeds if they're in 3D. These are described by 4 or 6 parameters, always. The 7 crystal systems are all primitive. Each of them has 1 lattice point per unit cell. And in the case of the 3D unit cells, each of them is described by 6 parameters: A, B, C, alpha, beta, and gamma. The Bravais lattices are also conventional unit cells. However, some of them are not primitive. Question: which Bravais lattices are not primitive? In what ways do the non-primitive lattices differ from each other? Luckily, we can always transform a non-primitive conventional cell to a primitive cell. For example, the primitive unit cell for FCC is rhombohedral, and you can see that there's 1 lattice point per rhombohedral unit cell. Now, the rhombohedral primitive cell is not unique. There are many other primitive unit cells for this FCC unit cell. However, any primitive cell you might choose for a given lattice will have exactly the same volume as the others, and it can be transformed into any of the other primitive unit cells. Recall the graphene model from part 1. The unit cell for this model is conventional, and it is primitive. However, this unit cell is not a good choice for electronic structure calculations. Why is this? Properties of crystals are determined by their symmetry, and it's the point group symmetry of a crystal that determines the crystal's properties. Electronic structure calculations are performed over the entire unit cell or a part of it, not the entire crystal, because what's in the unit cell repeats itself. The conventional primitive unit cell does not contain all of the symmetry elements of the point group. For example, it has no 6-fold axis. The conventional primitive unit cell that's used for graphene does not contain all of the symmetry elements of the hexagonal point group. For example, it has no 6-fold axis. Let's transform to a new unit cell for graphene. First, we want to visualize many lattice points and use these lattice points to find a new primitive unit cell. The Wigner-Seitz cell is that convenient choice of primitive cell for our problem. It represents the complete point symmetry of the structure, and it works well with electron wave functions to give realistic properties. We only need the lattice points to determine the Wigner-Seitz cell, so we can remove the unit cell for convenience. We don't need the atoms either, so remove those as well. Now let's get started. We first select a central lattice point and then use line segments to join this point to every lattice point near it, the 6 nearest neighbors. Next, we draw perpendicular bisectors to the line segments. If this were a 3D structure, we would use planes as the perpendicular bisectors to the line segments. Next, we extend the lines until they intersect. The perpendicular bisectors now enclose an area around the central lattice point we chose. Every point inside the boundaries created by the bisectors is closer to the central lattice point than to any other lattice point. The bisecting lines outline the shape of the new cell, which is the Wigner-Seitz cell, the smallest enclosed volume created by the perpendicular bisectors. And now we have our convenient unit cell, the Wigner-Seitz cell. It's primitive. It has one lattice point at the center instead of at the corners. It's a Voronoi cell. In other words, it fills space completely, and every point inside the cell boundary is closer to the central lattice point than to any other lattice point. This Wigner-Seitz cell is in real space, though. Next, we'll create a Wigner-Seitz cell for graphene in reciprocal space, where it is known as the first Brillouin zone. Okay, then we reviewed a few relevant facts about conventional unit cells, and we constructed a Wigner-Seitz cell for graphene in real space. Next time, we construct a Wigner-Seitz cell in reciprocal space. Leave comments, ask questions, and I'll answer them online.